Hi everyone. Today we're going to learn about big O notation. It's an easy way to estimate the complexity of an algorithm. This tutorial is a part of data structure and algorithm class. So what is code complexity? Code complexity is a function that shows how much more RAM and CPU needed to run an algorithm when the input side of the algorithm increases. For example, a complexity equal to n squared plus 2n plus 1 where n is the input side. It can be the side of an array. Code complexity is usually used to compare algorithms. A more efficient algorithm is an algorithm that produces the same correct result with less CPU runtime and less memory space. For example, n plus 1 is more efficient than n squared plus 2n plus 3. So why is it important to measure code complexity? It's important to measure and optimize the complexity of the code because the code that works in development environment with small input size might not work at all in production environment with large input size. So we need to know the complexity and always try to optimize. The next reason is to save CPU and RAM cost, which is the money you pay for server configuration. The third reason is to reduce wait time per result to improve the user experience. To demonstrate 3 points above, we're going to have a look at two algorithms which are going to calculate the Fibonacci number as a position n. A Fibonacci sequence is a sequence of numbers. The first number is 0 and the second number is 1. Going forward number is the sum of two numbers before it. 1 equal to 0 plus 1 and 2 equal to 1 plus 1 and so on. Our algorithm will take a position n and output the Fibonacci number at that position. For example, this one, if fib6 equal to 8. First, we're going to have a look at an optimized algorithm. The time complexity of this algorithm is n. I will run a few input sizes from 10 to 20 to 30, 50, and 1000. You can see that the responses from the algorithm is pretty fast. It's under 10 milliseconds. Now we're going to have a look at another algorithm which is not very optimized. I'm going to run it with the same input sizes for the previous algorithm from 10 to 20, 30, and at 40 you can see that is getting slow. It takes more than 1 second to finish. And at 50, it looks like the algorithm is not responding, but if I let it run, it's going to finish in more than 2 minutes. Imagine you visit a website and it takes more than 2 minutes to show up. That is a very bad user experience. Now let's have a look at the runtime table for both of the algorithms. The first column is n, the second column is the response time of the optimized algorithm, n, and the third column is the response time of the not optimized algorithm, 2 to the power of n. With small input size like 10, 20, 30, everything seems fine. With 40, we can notice that the not optimized function is getting slow. It takes more than 1 second to finish. With 50, while the optimized function works fine, the not optimized function takes more than 2 minutes to finish. That is pretty much useless for a web application. Above 60, the optimized algorithm works fine, but the not optimized function had crashed. This is why optimizing code complexity is very important. This is a chart to visualize the complexity of two algorithms. The time to run the optimized algorithm linearly increases when input size increases. Whereas for a not optimized algorithm, for one increase in input size, you have to double the time to run the algorithm. With very large input size from 0 to 1400, the not optimized algorithm looks like a vertical line. That means for one increase in input size, it's gonna take a tremendous amount of time for the computer to run. This is the reason why our application crashed with input size larger than 60. Even on a decently fast computer like this one with 6 cores and 32 GB of RAM, the application crashes on only 6 lines of code. In summary, we have two algorithms to calculate a Fibonacci number at position n. With the position 50 and above, the not optimized algorithm is useless, whereas the optimized algorithm works fine. This is why measuring and optimizing code complexity is extremely important. Now we know why it is important to calculate the complexity. Let's learn how to do it. The first method is line-by-line analysis. It's very simple. For time complexity, we count one time for each line of code the computer runs. For space complexity, we count one space for each variable or array element created. After that, we sum up everything and we got the time and space complexity. Let's have a look at this simple example to see how we can calculate time and space complexity with line-by-line analysis. We have an input array of numbers, length n. The process is we're gonna add 1 to every single element of the input array. And the output is the array with all elements increased by 1. We're gonna count from top to bottom of the algorithm. When this algorithm runs, this line runs one time, so time is 1. And one new variable is created, so space is 1. This line also runs one time, so time is 1. And we don't know the exact number of the elements in this array, so we're gonna return to counting the space later. For this for loop, this initialization will run one time, so space is 1. And this condition will be checked n time, with n is the length of the array. So that's gonna run n time. This line is within the for loop, so it's gonna run n time. And now we know exactly that our new array is gonna have the same length with the original array, which is n, so it's gonna give us space equal to n. And then this line is gonna run one time, so time is 1 and space is 0. After that, we sum up everything. For time, 1 plus 1 plus n plus n plus 1 equal to 2n plus 3. For space, 1 plus 1 plus n plus 0 equal to n plus 2. So the time complexity of this algorithm is 2n plus 3, and the space complexity of this algorithm is n plus 2. So if we run it with the input of 3, 4, 5, it's gonna give us the output of 4, 5, 6. Now let's have a look at another algorithm that produces the same correctness but more efficient. Let's count line by line together again. Same like above, the time complexity of this line is n and the space complexity is 1. This line is within the for loop, so it's gonna cost n time and space is 0. And this line costs 1 time and 0 space. So in total, time complexity is n plus 1, gonna give us 2n plus 1. And space complexity is 1 plus 0 plus 0 is gonna give us 1. And if we run this, it's gonna produce the same results that we had before. But notice that space complexity doesn't depend on n like the previous algorithm. This is a huge efficiency improvement in memory, because no matter how big the input size is, the memory cost to run this algorithm stays the same. We have learned about line-by-line analysis. Now let's learn about big O complexity. Big O complexity is just an asymptotic analysis of line-by-line analysis. It sounds difficult, but it's really not. Asymptotic analysis means we always assume that the input size is very large, and the highest order term is good enough to represent the whole complexity of the algorithm. So to calculate the big O complexity, we take in line-by-line analysis and we remove lower order terms. In this example, that would be for n plus 100. And we remove constant factors. In this example, that's gonna be 2. So for a line-by-line analysis of 2n squared plus 4n plus 100, the big O analysis is O(n) squared. It's much more simpler, and is believed to be good enough to represent the algorithm efficiency across the software industry. The idea of big O analysis is very simple. Here we have two lines, one is 2x plus 1 and one is 2x plus 3. These are the complexities of the increased algorithm above. You can see that with small input size from 0 to 10, these are the two separate lines. Then if we have very big input size from 0 to 1400, these two lines are almost identical. The low order term 1 and 3 doesn't mean anything when the input size is very large. And this is exactly the idea of big O analysis. For very large input size, we can just drop low order terms and constant factor altogether, and the highest order term is good enough to represent the complexity of the whole algorithm. Let's have a look at the big O analysis of the two increased algorithms. The first one is O(n) in time. The second one is also O(n) in time. So we say that the time complexity of these two algorithms are the same. Space complexity of the first one is O(n). Space complexity of the second one is O(1). Then we say that the second algorithm is more efficient than the first one in space complexity. Now let's talk about the bigger complexities, names and graphs. This column is a possible line-by-line analysis complexity, and this column is the big O complexity of this line-by-line analysis. And here we have a common name for this big O complexity, and the complexity is in the increasing order. First we have O(1), constant space, constant time. Then we have O log n. Then we have On, also called linear time, linear space. Then we have On log n. Then we have On square, quadratic time, quadratic space. Then we have O2 to the power of n. Then we have On factorial. And this is a chart to visualize all of those complexities. This axis shows the increasing input size to this direction. And this axis shows the increasing time or space needed to run this algorithm to this direction. By looking at this chart, you can see how fast CPU time or memory increases when your input size increases. So in your work, always try to optimize your algorithm in the excellence and good area. Now you have learned what is big O complexity, how to calculate it, why is it important. Remember to always ask yourself, can it be more efficient for the code you write? That will help you to become a much better software engineer. Thank you for watching, and I will see you in the next video.